It's great pleasure to be here again. I would like to thank the organizing committee to invite me to this great conference. So today I will talk about how the age exterior paint can give the toxic effect on the soil biota, especially the nematode. So first of all, I have to say that this is the international collaborative working. So the chemical analysis is done by my students, Dr. Woo Young-song, and the nematode experiments was done by Dr. Shin-Hong Kim. And this idea was proposed by the Professor Walter Waldman and the Professor Matthias Lillig and me. So thank you for the nice collaboration. So as you know, the microplastic is a big concern these days, especially in the water environment, but it also affects the toxic effect on the soil, and also cause the change in the soil structure, like here, the soil fertility and the microbe. And then it causes the growth of the plant, and the toxic materials can be uptaken by the plant, and it can comes to our body through the food chain. Among the source of the micropollution on the soil, after the tire, you can see here the paint particle. So it's hard to see, I'm sorry. But the paint particle from the building applied to the building, and this is the second most microplastic source in the soil. Then if you think about the component of the paint, it consists of the pigment and the additive and the binder. So especially the binder is the polymer, and it consists of about the 20 to 40% of the weight, and it contains the polymers such as the alkyd and the polyacrylate and polyolefin. So basically, you can regard the paint as the microplastic source. And there's some study on the toxicological effect of the microplastic from the paint particle on the aquatic environment, and it shows some decrease in the survival rate and the mortality in the ocean species. But however, there's a limited study on the toxic effect of the paint particle on the soil environment. And we also, our collaborator published the paper on the toxic effect of the microplastic additives. So if you remove the extractable additive by using the organic solvent, for example of the ethanol, then we have seen the decrease in the toxicity. So we can conclude that the toxic effect of the microplastic not only from the polymer itself, but it can come from the additive. So to study the toxical effect of the paint particle, we try to extract the organic and inorganic additive out of the paint. So from the pigment and the additive, we can see some inorganic element. So the inorganic pigment, or people use the anti-corrosion agent with the metal. And also we see some organic additive, not only the polymer, but also we have the plasticizer and the flame retardant and the biocide. So we want to know what is the toxic effect of the additive. So to obtain the old paint particle, we try to find the old deserted area in Germany. So we try to find, we get to the Eastern Germany area, which is at least 40 years old, and we collected the sample from the wall and the rails, and the right figure, you can see the paint particle we collected from the two different sites. So there's a difference in the color and the composition and the shape. So we grind them, and then we sort it out according to the size range. Then to perform the toxicological experiment, so we use the C. elegans as a model animal. Then after the synchronization of the developmental stage, we mix the C. elegans with the different concentration of the paint particle that we collected. Then we check out the survival rate after the different after 24 hours. Okay, sorry. And this is the result. So we check out the number of the offspring, and for the site 1, the paint color was mostly green and the red. And depending on the size, it shows the differential toxic effect. And interestingly, it shows the highest toxic effect on the middle-sized paint particle, 100 to 2050 micrometer. And also, it shows a relatively high toxicity with the lower concentration. On the other hand, on the site 2, we collected the paint sample, mostly is gray and green, okay? And you can see here then the toxic effect is much less than the site 1, and it shows the highest toxic effect with the smallest size, okay? So it's quite strikingly different from the site 1. So we try to understand what's going on here. So first, we, with the ICP-MET, we analyze the metal concentration from the different sites. So we measure the concentration of the chrome and the zinc and the lead, and here's the result. So the chromium can be used as the pigment for the green color. So if you, in the site 1, we see the relative high concentration of the lead, which is correspond to the red color in the paint. And we see the high concentration of the green pigment for the site 2, which correspond to the green color. So that makes sense. And also we see the zinc concentration, and that is we normally use for the antioxidant or corrosion inhibitor in the paint. However, we think that this metal compound is not the major component to induce the toxic effect, because this chrome and zinc is considered non-toxic because it's not bioavailable, which means it's not easily dissolved in water. Okay. And also, the lead oxide is soluble, but it's only high acidic condition, less than around the pH 1.5. But if you think about the pH inside of the nematode, which is about 4, okay, so it's not dissolvable. So although these three metal compounds is highly abundant, but we don't think it's the major component to induce the toxic effect. We also measure the concentration of the copper and arsenic, okay? And first of all, I want to say that the copper concentration is higher in the site 1 compared with the site 2. And please remember that the toxic effect here is higher in the site 1. And also we see this type of up-down bell-shaped the toxic effect depending on the size. And this arsenic concentration shows the bell-shaped amount to shape the concentration. And also for the site 2, it shows the highest concentration as the size of the paint particle decrease. So this size-dependent toxic effect matched well with the arsenic concentration. So here's the conclusion. So although we observe the high concentration of the chromium, lead, and the zinc in the paint particle, but because of the limit of the bioavailability, we don't think that is the major component to cause the toxic effect. But although the arsenic and the copper is relatively low concentration, but the trend of the toxic effect would, based on according to the size, well matched with this concentration. And the higher toxic effect in the site 1 compared with the site 2 can be explained by the joint effect of the arsenic and the copper. Then we also study the additive effect. So to study the additive effect, we regard the additive into 3 categories. The first one is the volatile additive, and second one is the water-soluble additive. The third one is the organic-soluble additive. So to test each one of them, we treated the paint particle with first the drying, only drying, which means that we remove the volatile additive. And we also wash with the water to remove the water-soluble additive. And we also did the ethanol washing. So we combined these 3 steps in 4 combinations, and we performed the similar ecotoxical experiment with the C. elegans. And this is the result. So it's very complicated, but here you can see the drying effect, which is indicated by the bright sky blue. So basically, the drying does not remove the toxic effect much, but if you drying with the ethanol, it shows the significant restoration of the number of the offspring. So we can say that this both water ethanol soluble additive contributing to the toxicity of the site 1 particle. In the site 2, we can see that the drying, once again, did not significantly change reduce the toxicity, but the water-soluble additive can reduce some toxicity for the site 2. So then, what might be the component of the additive? So to identify those compounds, we performed the LC-MS-MS analysis for the additive. And among the compounds that we detected, this monoalkyl amine shows the good correlation with this toxic effect according to the site dependence. So we can see this here. The upside down, the bell-shaped toxicity is well matched with the concentration of this alkyl amine concentration. So when we check the toxicity of the alkyl amine, it shows the corrosive and the irritant and the health hazard, especially for the monoalkyl amine. And in the previous slide, we see that the major component of the alkyl amine was the monoalkyl amine. Okay. Then how can this monoalkyl amine can be absorbed through onto the C. elegans? So once again, this monoalkyl amine has the very low water solubility. So we don't expect that it is well dissolved in water and then goes to the C. elegans. However, when this paint particle directly contact with the surface, skin surface of this C. elegans, then it can penetrate into the skin. Then it can cause some toxic effect there. So we have very interesting toxic effect depending on the size. So based on our result, we proposed the potential fragmentation mechanism of the paint particle. So after we collecting the paint particle, we grind them and then we sieve them according to the size. And if you take a look at this picture, and the site 1, it has a very thin layer of the red color paint and with the thick layer of the gray, okay? Then if you ground them, then maybe for somehow the gray layer is more resistant for the grinding. So you can see this, if you take a look at the picture, then the smallest size, like 20 to 50 micro size, shows a relatively homogeneous color between the gray and red. But if you take a look at the middle size, 100 and 220, 250, and it looks like mostly the gray color. So the reason why the middle size particle shows the highest toxic effect because of this color difference. On the other hand, in the site 2, if you take a look at the paint particle here, then it has the relatively similar thickness of the green layer and a gray layer. So when you grind them, then they mix them together almost equally. So there's no big color change according when the size of the paint particle decreased. So in this case, the toxic effect is mostly dependent on the surface size. So that's why the smallest particle shows the highest toxic effect. And it also, the gray layer, I think, give the more toxic effect. So that's why in the site 2, it has some thicker green layer. So that's why it shows the less toxic effect. So this is the summary of the organic additive toxic effect. So we found the high correlation between the abundance of the alkylamine, especially monoalkylamine, in paint leachate and the toxicity of the C. elegans. And we found that the alkylamine is widely used as a multifunctional paint additive. And this alkylamine has the toxic effect, mostly it's corrosive, and it's also toxic to aquatic environment. And the toxic effect may be possible through this thermal exposure of the alkylamine through the skin. Sorry. And so this is the conclusion of my talk. So we try to understand the toxic effect of the metal and the additive of the aged paint particle. And we found that the high correlation occurs between the abundance of the alkylamine and the toxicity of the C. elegans. Sorry. So we normally think that the paint particle is not the source of the microplastic, but even after decades of the application, so mostly the evaporation of the volatile compound, the paint particle can cause the toxic effect to the environment. And this aged paint particle contains the heavy metals and the chemicals, and that is well known to the toxic to the terrestrial organism. So we should regulate them here. Yeah. So thank you for your attention. Yeah.